which is where we're at, we are going to start looking at stoichiometry. And what stoichiometry is relating things through a balanced equation. And that's why in our last chapter we had to be able to write chemical equations, we had to be able to balance them, because now we're actually going to use them for something. We're going to really use them for their mole ratio. What these balanced equations are telling us is they're telling us the ratio that things are reacting in. So for instance, if we look at this reaction down here, we have aluminum oxide, and showing aluminum oxide going through decomposition via electrolysis into solid aluminum and oxygen. So what this is allowing us to do, if we look at the mole ratios, is telling us that if we have 2 moles of aluminum oxide, then we will produce 4 moles of aluminum and 3 moles of oxygen. And that doesn't really seem like much for us, but that is what it's telling us. What that's going to allow us to do is to convert from any amount in the balanced equation to another one. So say we started with 100 grams of our product, or of our reactant, I should say, aluminum oxide, and we wanted to know how much aluminum we would produce. Well, we could convert this into moles, we could use that mole-to-mole ratio, and then convert this out again into a mass. And that looks kind of messy, so let's look at kind of a chart of how to do this. So what we've done before is we've taken masses of things in grams, and we've converted them to moles of things. And notice what we've used to get between those is a molar mass. So we can convert from mass to moles, moles to mass, using that molar mass. So notice that's what this is too. Mass of an unknown in grams. Get a moles of unknown in moles. How do we convert? Well, we convert using a molar mass, which is in that units of grams per mole. And this also over here is in units of grams per mole. So the way we convert between these two substances to convert between these two substances is to find that molar ratio. And this molar ratio is from that balanced equation. So what we're going to be able to do is we're going to be able to take a mole amount or a mass amount of some reactant, and we're going to be able to solve for a certain mass or moles of product that we're going to make. So I'm going to kind of reference a chart like this when I'm doing these types of conversions so I can keep track of where I'm at. So let's just look. This is one of the questions in your book. It says, write all the possible for all these chemical equations, write all the possible mole ratios. Well, we can do that, but let's use these for more typical problems. Say we want to make, or say we have 10 moles in the first equation of mercury oxide. And say we want to know, well, how much oxygen is that going to produce in moles? So we'll just do some conversions in moles first. So I have 10 moles of mercury oxide. I'll know how much oxygen that's going to produce in a mole amount. Well, again, if I look back at this, if I have moles of a given, if they give me the amount of moles, it's a one-step conversion here through the mole ratio to the moles of an unknown. So it's a one-step conversion, one arrow I have to cross. So I have my moles of mercury oxide, and now look at what this ratio tells me. 2 of these will produce 1 of these. That is my mole ratio. So if I have 2 moles of mercury oxide, I'll make 1 mole of oxygen. And notice this is the beauty of dimensional analysis, is now I'm not just multiplying or dividing, I'm doing a conversion between different types of molecules, different types of compounds. So if I have 10 moles of mercury oxide, notice 10 divided by 2 times 1, I'm going to make 5 moles of oxygen. Okay, pretty easy. Let's clear it. Let's try something else. How about number 2? So we have ammonia. It's reacting with some nitrogen monoxide, making nitrogen gas and water. So, maybe our question would be, how much nitrogen monoxide is needed to react with, say 20 moles of ammonia? So notice what we can do. We don't just have to solve for products all the time. We can also solve for how much is required to react with what we have. So I'm going to start with what we have. I said I have 20 moles of ammonia. So if I have 20 moles of ammonia, and I want to know how much nitrogen monoxide is going to react with it, and again, if we're talking about amounts, how much typically in moles, again, this is just a one-step conversion looking at that mole ratio. Now, what is the mole ratio between these? Well, 4 of these are going to react with 6 of these. So I'm going to put the 4 on the bottom because that's the amount tied to my ammonia. That will cancel out my ammonia amount, and that's going to react with 6 moles of nitrogen monoxide. So if I have 20 moles of ammonia, I need to make sure I have, let's go through these numbers, 20 times 6, 120 divided by 4, we're going to get 30 moles of nitrogen monoxide. And at first, that's all we're going to be wanting to do. We're going to want to just look at these mole ratios and say, hey, if I have this many moles of this, how many moles of this am I going to make? However, pretty soon, and that's what we're going to focus on in the next chapters, we're going to take a mass amount and go all the way to a mass of something else. So maybe we can do that here with C. Say I have, 100 grams of aluminum. And I want to know if I have 100 grams of aluminum, how much, so question mark, how many grams of sulfuric acid do I need to react with it completely? So I have my mass of aluminum. I want to know, I want to react it with sulfuric acid. I want to dissolve it, make aluminum sulfate. How much sulfuric acid? And you can see the importance of this. Sulfuric acid is a very toxic type of substance to have lying around. We don't want to use any more than we absolutely have to. So if we have a certain mass of aluminum, see if we can't solve for the mass of sulfuric acid that needs to react with it. Exactly. Well, if I have a mass, and going back to this chart, there we are. Let me clear things off. Now I'm given a certain mass, 100 grams of aluminum. Now notice I can't convert directly to a mass of my unknown, my sulfuric acid. What I have to do first is I have to convert it into moles using the molar mass. Well, I'm going to rewrite this here so I have room, and I'm going to try to write it cleanly, 100 grams of aluminum. Now, if I want moles of aluminum again, I'm going to have to go back to the periodic table. So here's my periodic table. Find aluminum. There's aluminum. And again, it's molar mass. So hopefully we can all find molar masses. I'm going to round this one off to the 100th, 26.98. Now that we're doing mole conversions, I'm going to be a little bit more particular about making sure we go at least to the 100th. 26.98 grams of aluminum. Remember, that number is always in grams. It's always in 1 mole. Notice I put it on the bottom because I want to get rid of my mass units. I can't relate masses to masses because all of our molecules have different masses. What I have to do is convert it into moles first. Notice I'm not going to stop and do this calculation. I'm going to keep going with it, but I'm going to add the next step. Now that I'm in moles, so if I actually divided these numbers, I would get a molar amount. Now that I'm in moles, just like I did in the last one, I can convert to moles of something else using the molar ratio. So let's do it. What is the molar ratio between aluminum and sulfuric acid? Well, it is 2 aluminums react with 3 moles of sulfuric acid. That goes in next. Notice my 2 moles of aluminum are going on the bottom. The reason they're going on the bottom is so we can get rid of these units of moles of aluminum. Moles of aluminum. The only way I can put that on the bottom, though, is if I have the moles of sulfuric acid on top. And again, this question is asking for us to solve for the mass of sulfuric acid. That's why I'm going to mass of sulfuric acid. But notice I could also solve for the mass of aluminum sulfate I'll make, or the mass of hydrogen gas that I'll produce. So I have 100 grams. That's what I'll start with. I converted it to moles. I used the mole ratio to convert it into another substance. So it's going to be molar mass is my first step. My second step is going to be mole ratio. Last step, I want this back out as a mass, so I'm going to have to look at the periodic table again and add up the mass for sulfuric acid. So it's 2 hydrogens, a sulfur, 4 oxygens, kind of a big mass. The mass is 98.08. Again, that's in grams. I want an answer in grams, so I'm going to put that value on top, 98.08 grams of sulfuric acid. That is what I want. 1 mole of sulfuric acid is what that amount is in. So now I have my answer set up. Notice molar mass, first calculation, mole ratio, and then we end again with molar mass. So we're going to have this pattern for a lot of these problems. Now, sometimes they'll just give you the mole amount. Sometimes they'll just want the mole amount. But a lot of times what we have to be able to do is convert all the way from a mass of some reactant to the mass of either another reactant reacting with it or perhaps a product. But there we have it. These are the problems that we're going to be spending a lot of our time from here on out doing. Now if I just calculate this across, no, it's not very hard. We have 100 divided by 26.98 times 3 divided by 2 times 98.08. And my answer comes out fairly large. We get an answer here of 545.29 grams of sulfuric acid. So notice it has a 3:2 ratio, so we need more of it. And also, it has a much larger molar mass than aluminum, so we're going to need a lot more sulfuric acid than our mass of aluminum for this reaction to completely occur.